I was going a bit fast yesterday on large deviation, so we go back a moment there. Just to, so large deviation for 542 on R. So, by the way, do you have questions in general? I will revise a bit what we did for large deviation, but if you had doubt, new ideas, you have ideas to solve my problems? No? So I will maybe mention some, I mean, there are a lot of open problems in this field because essentially the only people working on this field is me and my ex-student, Barashko, in this particular approach. But I like it very much. So one day other people will understand that it's nice. Okay? Yeah, I just have to wait a bit. So large deviation was this problem. Okay, essentially I rephrase in other words. Essentially it's to study the problem to study this particular. So for 542 is this particular measure. I've write it a bit more formally, okay, but just to understand what we are doing, because this parameter appear in a very specific way. And essentially you want to understand, is to understand this infinite dimensional integral, if you want, okay? So some kind of integral like this. You want to understand it when h goes to 0. F is just a test function, so you want to understand for a large class of function. And S is, S phi is the usual thing, is 1/2, like this is the Gaussian free field with mass 1. And then you add maybe the 4 power, and then maybe you subtract the renormalization. Okay, so I write it formally just to go back to our somehow. This is what we are doing, and then you want to understand the log. And if there were no fluctuation, this would diverge with h bar, so you want to take h bar and you want to understand this limit. Okay, so the problem in large deviation can be summarized. I don't do an introduction on large deviation, okay? It has a lot of application. But for us, large deviation means I want to understand this particular limit. This limit has a meaning in physics. This is called the semi-classical limit. This is why I have h bar. In quantum mechanics. Okay, so this is related. So I told you Euclidean quantum field theory are related to problem in quantum mechanics. And then if you track in quantum mechanics, there is a quantity, which is h bar, is Planck constant, which it's related to the size of quantum effects. Okay, in the real world, we don't see quantum effect. This object has a position and a speed. But somehow in the quantum world, that's not the case. Somehow you cannot measure both at the same time, and this is the precision of that measurement, okay? And therefore, when you track all these things into the Euclidean domain, you end up with the measures of this kind, okay? H bar appear in this position. Usually we forget about it, we put 1, but now we want to bring it back, and then we want to understand a limit where somehow you're looking at phenomenon, at fluctuation, where the scale of the quantum effects are very small, okay? And this is called the semi-classical limit. And you see that in this limit, somehow you want to concentrate around classical solution of this variational problem, okay? The original variation problems. Okay, so the result somehow that we want to say is that this variational functional, so is the infimum over all functions. So let's say you can take S prime of Rd, but they will be better, okay? Because and now essentially you get exactly what you have here in this formal. So this is, if you want, the justification of this formal formula, which is very heuristic. We gave a precise definition of what we are doing, but I wanted to go back because then you see exactly what you should expect, and this is the reason why somehow this is minimization, and you minimize exactly the integral of the Dirichlet energy and then phi square, and then lambda. If you put lambda, you have also lambda phi 4. But there is no renormalization, okay? Because now you have, in this semi-classical limit, you don't see the renormalization. Okay, this was the result, which you want to prove. In some sense, Boué-Dupuy formula and the variational approach came from the universe of large deviation. It is a tool which was devised and for doing things like this, because you see that you expect that in the limit you get a variational problem. So you want to express the probability as a variational problem so that you have the same object and it's easier to take limits in that way, okay? So this is a very interesting approach to large deviation. If you know large deviation, there are other ways to do it, but somehow this is very natural to do. And so I wanted to do, sorry, this is R2. So again, okay, this is the formal expression. What we did yesterday was to construct a family. So this is the 542 measure with parameter h on R, okay? And of course, is not unique because I cannot prove uniqueness. This is open problem for you. Again, for small lambda, it should be unique, but I don't know. Therefore, I just add A, okay? So for any value of h, you choose one of those measures that you get as accumulation point of the finite volume measure, and then you want to understand now the accumulation points in this parameter, okay? You want to show somehow that this measure concentrate in such a way that this integral become as the value of this variational problem, okay? So what we did, please ask if it's not clear. Okay, so this is the goal. Essentially, you have to do with this measure. So this problem become to take the limit as h goes to 0 of h bar log. So yeah, and then you have the integral. This is the test function. So you have to do this for every test function. Okay. Because then this identifies really this part. If you do it only for a test function, it's a number, so it's difficult to see exactly what's going on. But here, essentially, you have to take now this limit. This is precise. Okay, now this is precise. I constructed this measure. I look at this object, divided by h bar, and I want to compute this limit. Okay, so this is what I want. This is my task, and you see the measure. If you just construct the measure, you are lost, okay? At this point, you don't know what to do but we don't have only a measure. We didn't only tightness. We have a description of any limit point. So we have a description of h bar. So h bar is related to a solution. This is our of the equation. So a solution Z, if you want Z h bar of the forward-backward as this. Okay. It's not a good name because forward-backward as Z mean many things, but in this course we mean just the Euler-Lagrange equation for the limiting. Okay, and I told you. So we know that this measure, it's related to solution of this problem, which is like that. So you have the potential over all R. I don't rewrite everything, but somehow. And then you have W1 plus Z1, and this is Z1H. This is also, the potential also depend. The potential does not depend on H. The only thing that depends on H in this thing is the Gaussian free field. So there is an H in front of the Gaussian free field. And then you have the usual bilinear form for which measure the entropy. Sorry, this is K1. Okay, so you are testing. I will use this a lot today. Okay, so let me know if you want to have more. Okay, and this should be true. This should be true for every test K, okay, which was in H1 of space and time. Okay, so this is the description. This is the description of nu bar, in which sense that this is the law of exactly W1 Z dash. Okay, so the claim is there exists a process which a terminal value as this measure nu, describe the measure mu, and it satisfies this property along the trajectory. Okay? Yeah, please.
This integral with lambda psi to the 4 for psi s prime is just infinity in your heuristic here? Because it's psi is a distribution?
Well, but if it's infinite, I mean, this is a minimization problem. So telling you that you just have to concentrate on H1 and L4. Yeah, yeah. And phi is a f. You can find you just use nice bounded functions, okay, of distributions. Okay, these are just test functions. You are, to understand large deviation, you have to understand this limit for a large class of phi, not all, but a large class. And actually, we will take specific phi which are convex. They are enough because they. You see, if you put here something which is like a Gaussian, which concentrate around a point, and you can move the point, is enough. Okay, but I will mention this later. Okay, so this is our tool. Okay, this is what I wanted to advertise. So, want to show that large deviation. I'm not interested right away in large deviation, but maybe you are, and I want to show how you use this information to extract this large deviation statement. Okay, it's a bit weak, so we have to work more than we should, because somehow I don't know that this equation. This is an equation, okay, because you have infinitely many constraints, each one for every process k, and you have to think this is like a weak formulation of one equation, and then if you understand a bit PDEs or ODEs, you might hope that there is only one function z which satisfies this for all kappa. Okay, unfortunately I cannot show that. This is the problem of uniqueness of this measure. I think it's true, again, for small lambda should be true, for small potential should be true. Probably it's also true when h is small. I was discussing yesterday with Justin. It was observed well, but the variational problem is unique because it's convex. So why? The point is that it could be that maybe uniqueness is also true for small h bar, okay? So open problem, okay. So if you want to open problem, is z bar unique for small lambda or small h bar, okay? If you want problems, this is exercise for you for homework. Yeah? I don't know, maybe for me it's difficult. Then you believe it's a homework and you do it and they say, it was very easy. Okay? One problem less. Okay, yeah.
Should there be a square root of h bar?
Yeah, you're right. Perfect. Thank you. This was to see if you were attentive. Yeah, thank you. Yeah, sorry, because I want to write in this way because this is the usual GFF. This is the usual GFF we introduce, like this dynamic version of the GFF. And you see that here the covariance is weighted by h bar. Okay, so h bar will appear as we discussed. Okay, so this is a small noise limit. So large deviation is a small noise limit for the BSD, okay? BSD, forward backward. And I was a bit fast, but I will be fast again, but a different faster. So maybe there are the full proof and there are technical details, but at least we want to, what we expect, how we get to that, is that you see the noise appear here and appear in the weak polynomial because this object then it's a product of weak polynomial time powers of z. Then every weak polynomial is multiplied by h bar. H bar is going to 0. You have tightness because the kind of estimate I did to estimate the size of the solution will work. So you have tightness. You have estimate uniform in Akka. So we have estimates. So we have estimates uniform in h bar for z. This gives me tightness for in the natural space is like this space H1, a bit less than H1 space, okay? You have tightness for this sequence. There you can extract limits, okay? So we can extract limits. Accumulation extracts accumulation point. Let's say Z naught, okay? I call one of those accumulation. Again, there is no uniqueness. I have only tightness, and I take the limit, okay? So, and now you guess that if you have enough control of the sequence, you can prove that this converges to the limit which you expect. So the only thing that will happen is that this will disappear. Okay, so for Z, I said Z naught satisfy an equation which looks like this. There is no W anymore. There is Z naught. There is kappa, and then there is the quadratic form. Okay, so this is for every kappa again. Okay, kappa, again, it's a process, but now you realize, okay, in this equation there is no noise anymore. Okay, noise disappears. Noise is like an SDE. The noise is something coming in and which gives you the randomness. Okay, there is no other source of randomness a priori. This is not strictly true because we had in the notes, everything is done in detail, and to have minima, you have to relax the problem, so you live in a larger probability space where there could be more randomness. Okay, relaxation gives this problem to you. It's like in optimal transport. The optimal transport map, there is no additional randomness. One point goes into another point, but when you relax the optimal transportation, you have transportation plans, and there you can use more randomness to decide what is the plan. So a priori here, the probability space is larger than the probability space of W. In the notes, it's written this way, and then you have this variation. But let's forget a moment. It's not essential. It's just a small nuisance. It will not change. You have a problem like this, and okay. And somehow this was where I started to go faster. I need to understand what's going on here. So what I can do, somehow I need to relate this to this functional in some way at least, okay? So here we are at the level of the Euler-Lagrange equation, okay? Now, you see, we are looking at the Euler-Lagrange equation for those objects, and I will get some Euler-Lagrange equation for that. So then I have to integrate to go back to the functional, okay? So this, we have to do some work because we don't work directly with the functional, because there is no functional in the here because we are in infinite volume essentially. Okay, at the beginning. Well, we could have, but we'll discuss this maybe later. Okay, so let's go here. Let's see. This, by the way, makes sense. Again, think because K you can choose compactly supported. Okay, so this is a local condition on my process. So yeah, the first thing I observed is that you can take essentially, let me see what I want to say. Yeah, here there is no real randomness. So you essentially what will happen is that Z0 is essentially a deterministic function time S. Okay, you have to do a precise argument, but this is the result. Okay, so. You prove that essentially it's concentrated around a deterministic function. And when you do this, this energy become, yeah, you do the same also for kappa. Okay, kappa you can choose. So you choose S time another phi, and in psi. Okay, and then the energy become. You compute this energy, and the derivative is just this function. So when you integrate, you just get somehow like psi with phi. Okay, let's say you take this psi compactly supported. Okay, to get a finite. Okay, phi you don't know that it's compactly supported. Okay, but you can take the psi compactly supported, so you compute this quadratic form and you get that. And now you compute you compute, this is the gradient of V1, K1, so these are just, you look at this object in the limit and it's just the integral of phi cube psi. Okay, maybe there is a 3, but let me put, no, I think, yeah, let me put a 4, otherwise I don't get this. Okay, you have to adjust the constants. And, sorry, I continue to make the same mistake, is because, yeah, this is the measure nu, okay? So this is about the measure nu. Sorry, I'm making always the same mistake. But I don't want to study the limit of the measure mu, so now I want to study this limit. And you could say, well, the measure z represents the measure nu, so I just integrate this function over z, but this is not easy to do because you would have to prove that this function, I mean, is not easy to control. The good way to look at this object is to say, well, this is just a different potential. It's just the same measure, I mean, a measure with a different potential, okay? So what I'm interested in is not really this, but is the same object with the gradient of f, okay? So essentially, you want to add here the gradient of fz, k1, okay? Because this is just, you go from the potential v to the potential v plus f, okay? I will, okay, let's assume this is the right thing to do, okay? I will, maybe I will spend a bit to discuss this after we finish that. And then you have, so you have the potential, but then you have also the gradient, okay? Then you have the gradient of f z1, 0 is just the integral of, well, yeah, is just what it is, okay? The gradient of f in phi times psi, in the direction psi, okay? So this is a functionally, you take the directional derivative, okay? So you have these 4 terms, and then this has to be true for every phi, so this gives you an equation, essentially give you an equation for phi, okay? It gives you that this plus, let's say, 4 phi cube plus gradient f phi, it's 0, okay? If I would not put f, well, this equation has solution 0, okay? It's an elliptic equation. You can prove that it has only solution 0. So this is because I need to probe various points. This is why I want different f. Okay, so I got the limit, and then essentially you prove that the limiting process has this form and satisfy this equation, okay? And now you realize, okay, even if this was a limit, so there could be more than one limit, the limiting equation you get is unique. This has only unique solution. So this first order condition, it can be satisfied only by one function, okay? Because, okay, we can prove this, okay, maybe, okay, because I will need the same argument later for the exponential. So let's prove that if f is convex, this has unique solution, okay? So this is the next step. We, again, remember, we have to fight with the fact that we don't have a lot of control of those measures, okay? So unfortunately, no, and so this is an accumulation point, okay? This is, yeah, not unique, if you want. But then you do this argument and you prove that it has this form, and then that the function phi has to satisfy this, and then there is only one function phi, okay? Assume f is convex. For example, we can take f of phi to be things like some norm of phi minus some fixed function, let's say phi bar squared, yeah, something like this, some norm, some negative norm, I don't know, like minus 1h with some weight. Something like this, okay? It's not very important which norm you can use. Okay, just something that makes sense in the original problem. and then with a fixed phi bar. Fixed. And then you prove, somehow what you have to prove is that a priori for large deviation you have to use all f, but then there is a result, say, if you use this class of f for all psi bar, then it's enough to, maybe if you put, you have to put a constant here. So this class for every psi bar and every constant is enough to determine the result of large deviation for any other f. Okay? But this is because these functions, you see this function, if they are in the exponential, they look like some bump at the function phi bar. Okay, so they are just reducing the integral in some region, and when you know the behavior of the integral in every region, you know how to behave large deviation. Okay, it's not very important. But the important is that I can choose f convex without loss of generality, so I can use also this acronym, so let's assume that. Okay, the following are equivalent. No, I'm joking. Okay, no, I'm not. So if f is convex, then there exists a unique phi. So maybe let's do this because it's, I forget the constant, it's not relevant. Okay, so there is a unique phi which satisfies this equation. What I cannot do what I cannot do here, and here I cannot do because this potential is not convex. Here I can do because the renormalization disappeared. Okay, this is very important. The renormalization is what creates the problem. How you prove that it's unique? Somehow you you compare two solutions. Okay, this is very similar this path coupling argument of Justin. So you look at you assume that there are two solutions, let's say phi and phi prime. You look at the difference, let's call delta phi minus phi prime. You compute here, okay? So you compute, so if phi prime also satisfies this equation, then you have that one, you take the difference, and then you have here, you have phi cube minus phi prime cube. And then you have here gradient of phi. Minus gradient phi prime. And this is 0. And now you have just to do one thing, which is what I do here now. So I take the difference. You see, when you want to prove two things are together, one initial strategy you can try certainly is to prove that the difference is 0. So the difference delta satisfies this equation, and then now if you want to prove that it's 0, you can try to multiply this equation with delta itself. Okay, you try to make it this positive. So you can try to multiply by delta to get that 0 is, and then you get you multiply by delta and you integrate, and you get here, then you integrate by parts, so you get a quadratic form. Okay, this is delta square. Then you take delta square from the 1, and then you get the integral of phi prime phi cube minus phi prime cube time delta, which is phi minus phi prime, and then you have the same thing for the other function. Okay, and here you use the convexity. Okay, and then you use to prove convexity, give me that these are positive. Okay, yeah, because they are I mean, this is the derivative convex function. Did I made a mistake? No, I think it's correct. Okay, so phi 4 is convex. So this is the derivative of the convex function. So the second derivative is positive. So this at least is bounded below by a positive quadratic form. Okay, so you will have that. So these terms are positive. So the 0 is smaller, no, it's bigger than this. Okay, and then you're done. Okay. and then you're done. Okay, this implies that delta is positive. Okay, if I had the strict convexity, I could have dropped the mass, but you see, this term now starts to be important for us. Okay, because if it was not there, then you just can deduce that the function is constant, but not that it's 0. Okay, and here I'm using convexity. Okay? Here is where convexity plays a role. Okay, so this proof is very easy, but it's the pattern for next proofs, so it's useful to use. So this gives you uniqueness of the, so this object is unique, okay? You prove that the family, each of these objects is maybe not unique, but when you remove H, you converge to an object, you look at the equation, and you realize that it has a unique solution, which is deterministic, actually, and depend on the function f. Okay, now I realize that I skipped this part, but I feel a bit uncomfortable to skip it, so we really looked, you see, I looked at the equation for a modified energy, and you say where I'm supposed to use this information now. So I think this gives me the opportunity to talk about this part. So at this point, we have, so essentially we obtain a unique, so what we found essentially is that phi, given f, I have a unique phi. So I call it, so since it's unique, I call it phi f. Okay, for every function f, you get a unique phi. Okay, so now you say, okay, where I'm supposed to use this, we have to understand a bit the connection between integrals and this quantity. So let's go back a moment. Yeah, take here. Now I'm a bit lost. I should have done this before, sorry. I think this is, but this is it's a useful observation, so maybe I want to spend a moment to discuss it. Okay, so how do we say, parenthesis, a remark, so let's, an intermezzo. So we stop a moment to discuss this. Let's go back again, or maybe never, it depends, let's see the time, but the intermezzo is about, yeah, it's about these perturbations that I'm doing, okay? This is an important point. So let's go back to the general framework. So the setting, so you go back to the general setting where you're looking at measures. So I'm defining these measures like with a reference measure, like this. So this is more general. So I will, before even applying to phi4, again, okay, we want to consider Gibbs measures. Then you have this. We had written the variational problem, and then we wrote also that, remember, okay, you have that minus the log of the integral of this exponential with respect to the measure is the inf over, let's say, the z of vf of z, and vf of z was the expectation of the potential on the shift plus the quadratic form. Okay, so this was our general setting adapted to the two-dimensional case, but just to be definite, okay? And then if we have minimizers, okay, the minimizers, which I call ZV, satisfy the first order condition, okay? And this is V prime, let me be right, K plus Z, okay. Okay, so we have all this. Now, I want to understand, now you see in large deviation, but in many other cases, now I want to understand things like this. Okay, I have my measure, and I want to integrate an exponential function, okay, of my measure. This is, maybe I want to prove that this random variable has exponential moments under the measure, okay? This is useful. Anyway, I want to have a technology that tells me to compute these integrals, okay? Because it's useless to have a measure if you cannot compute things under the measure, okay? So this is natural. Now you go back and you see, so if I give a name to this quantity, let's call it W, well, actually, let's not call it anywhere. Sorry. If I look at this object, what does it, and I take the log, and maybe I take the minus, what does it look like? Well, this measure creates another part in the exponential, and then the constant here is just another integral. Okay, so you can write this as minus, so this is a triviality, but let me write it anyway. So there is this part and the potential which give you this, and then you have to subtract the denominator, which is just, sorry, here it's minus. Okay, which is just something like this, okay? So if you call this quantity, you call it, yeah, I don't, okay. So you see, you just need to compute quantities like this, okay? So this quantity is like that with the potential F plus V, and this quantity is like that with the potential V. So I can write this integral. I can write as the inf over z of f plus f of z minus the inf over z of fv z, okay? Because it's just the difference of, okay, this quantity is represented by this formula. This quantity is the same formula, but with a different potential. You agree with this, or did I mistake? Okay. And actually, this is the beginning of the computation to okay, so let me, now what are, so if I assume the inf is attained, which I can do if I relax the problem, I can write this as follows. So this is, let me see if I want to do this. Sorry. Yeah. Let me think a moment what I want to do now. I have different way to proceed. Yeah, okay, let me do one thing, okay, because from this you can deduce many things. The first thing you can deduce, for example, so you have this equality, okay, so this quantity, so the first moral, let me give you the main message, because I have, maybe there are too many computations to be done to realize, but this is important, because somehow it was important to realize that, you see, this is the right way to estimate this quantity in this framework, okay? When you have a measure which you represent in the variational approach, and then you want to compute some average of a quantity of this form, maybe you can write your quantity in this form, it's not wise to use the information you obtained and try to push it through to estimate this, because this object is very difficult, okay? You see, if you remember from last week, from yesterday even, the estimate we have on the variational problems, the estimate on Z are very weak. Maybe we have a second moment estimate. So there is no hope to estimate anything interesting with that. So the right thing to do is that you realize that this object can be controlled if you control a perturbed variational problem. Okay, you see, because now you can say, let's say this is the quantity of interest. I call it, in the notes, it's called WVF. Okay, because you think that V is fixed and F varies. So now you have to estimate for WVF. So you have an upper bound. How you get the upper bound? Well, here you put not the minimizer, and here you put the minimizer. Okay, or you have a lower bound if you do the other way around. Okay, so here you have an upper bound. Now, what is a good non-minimizer to put here? You can put anything to get an upper bound, but of course, it's very smart, since you have this other object. Here you can put the minimizer of that problem. Okay, so you have an upper bound which looks like this: Vf plus Z, Zv. Okay, this is bigger than that because this is the infimum overall. But this is now Fv, Zv. It's exactly the minimizer. Okay. And then you have a lower bound in the other way around. Okay, so you have F plus V. Here you have to be tight, so you put exactly the minimizer for the perturbed problem. And here you can be slack, okay, because you have the minus sign. Okay, so you have an upper and lower bound in this way. And these are useful. Okay, so if you want an upper bound on this quantity, this is what you have to do. Okay? So this gives bounds. And I think this is, yeah, this is, sorry. This gives bounds. And then there is another relation. This gives bounds. And you say, okay, it looks complicated, but look, this is now nice. It's not only a difference of two numbers. Let's say you look at this, for example. Let's say this is ZV. This is the upper bound, for example, okay? So you don't have to compare these two numbers. What are these quantities? Okay, so this is the expectation. The first one is the expectation of V plus F on this point minus the expectation of V on this point. And then there is the quadratic form. But the quadratic form here is the quadratic form of Z. And here you have the same thing. So they cancel. So everything cancels. And this is exactly the expectation of F on ZV. Okay, because everything cancels if you do it this way. Okay, so you can bound W lambda F. For example, this is one thing you get from this. The upper bound is like that. And the lower bound you can guess what is the lower bound. Okay, so the lower bound was like this, okay, because here I minimized and here I was slack. So here now you have a different process, but essentially you see everything cancel again because they are computed in the same point. So V and V cancel, the quadratic form cancel. The only thing that is different is the F. So you have the similar expression. Is not nice. You don't like it? I find it amazing. Okay, you have two bounds. So you see this is the exponential functional, and then you have two bounds like this. Okay, actually you can do more precise. You have a variational formula for this written in terms of this shifted variational problem. But I want to give you an idea how you use this form. And then there is a better formula, which is like this, which is a precise. So this number is between these two numbers, And then actually, if you do some computation which are in the notes, you realize that this number is exactly the average of all the things you meet along the way between these two quantities, okay? So essentially, it's the average between 0 and 1, the alpha of the expectation of f of z v plus alpha f. Okay, now you put a number alpha in front of the f, and you average all the things you see between 0 and 1. 0 and 1. Okay? And in the notes it's proven in few lines, but I don't want to do it. So you have a formula like this. So you can recover this expression, so you can recover the value of this integral. You see, you can exponentiate f by solving a family of variational problems. Okay, this is maybe the connection I wanted to give you. Okay, sorry, this is v, not lambda. And again, these are tricks you do. Actually, we played with this quantity, and they came out this. This is quite natural because this is, you see, you write this, and then you try to get through this computation, upper and lower bound. But then you realize you have this quantity, and actually you have other quantities, okay, in the sense that you have also an expression like this, because I told you that ZV has the law of nu, okay, so you can also express this quantity as minus log the expectation of exponential minus FZV, okay, so you have a lot of relation between these quantities, okay. But this is because ZV has the law nu, okay, so this is exactly an easy formula. And this somehow is some kind of differential version of that formula. Okay. This is useful now for our large deviation. Sorry, I tend to switch. Okay. Now let's go back. So the intermezzo is finished somehow. Maybe I will give you okay, let me give you a consequence of the intermezzo, just to give you a feeling how you use it. So exponential integrability. So I'm using it to show you that it really gives you something. So think about take z the minima, let's say take z the solution of 542, a solution for 542 on R, okay? This is the measure we constructed. I don't think I should give a good definition. I don't have good names to talk about this object. This is just the z which represents the 542 of R, which we constructed. Okay, so in particular, the law without h, okay? We forget about h in this moment. I don't want. So the law of W plus Z is exactly 542, okay? 542 over R, or A 542 over R, okay? Again, remember that I don't have uniqueness, so I have to continue to remind you that we just take one limit. So maybe I need to say, I should have written this, okay? This is one element of the limiting point of 542, okay? Whatever it means. And then imagine that now I want to prove that your measure nu, yeah, this is nu, this is the law, the 542 on R. So imagine I want to prove that 542 integrates exponential norm, okay? I want to prove that this measure has exponential tails. Okay, this is a reasonable property. For example, if it was the Gaussian free field, I could integrate somehow with a small number, with a small theta, let's say. I could integrate maybe, let's say, h minus 1 with some exponent with some weight at power 2. Okay, for example, I know that this is true for the Gaussian free field. Okay, so Gaussian free field for small theta, if theta is small. Okay, for the Gaussian free field, you have this property. Now you would like to have a similar property for this measure. Are our approach strong enough to get this information or not? So you actually here you can do better. You can do yeah, here you can do better. You can take fourth power. Okay, so let's say this is some weighted space. I mean, if you complain, you say which, I tell you for a reasonable weighted space, okay, and appropriate, the one which works, okay? There is at least one who works, okay? I like this word reasonable. Everything works better if we are reasonable. But the point is, this you cannot do for Gaussian free field, okay? You cannot put 4 here. Gaussian free field at most integrate small exponential square things, okay? Because they, even infinite dimension, it will not be true, so with the 4. So this is a specific property of this measure which does not have the Gaussian free. So is it true? So is this true? Okay, so I think this is even more interesting than large deviation. Let me continue. Is this true or not? What time is it? Yeah. And now you use this idea. Okay, you use this magic bound. Okay. No, actually, let me see which one I want to use. I think I want to use the other one. Well, yeah, here, now I confused you because traditionally I put the f is put with a minus, okay? So but now I want somehow a bound. So when you want a bound, you want to change all the sign. If you start to change all the sign, the inequality which is important to you is this one, okay? Because you have to send f into minus f, so the two bound switch. So I have to control this one. So essentially what you have is that log of the integral of this guy, phi 4, h minus 1 rho, nu d phi is smaller. Okay, now I'm using this formula. This is smaller, so I took the log to bring the thing down. This is smaller than the expectation of this function. Okay, theta, then the norm, h minus 1 phi to the power 4 on, yeah, sorry, here I've been, I forgot to put plus w, okay, of course, because the function is on phi. Is the same here. Yeah, sorry, I forgot everyone. Just the full field, okay? So here you have to put the full field. You have to put W1 plus Z1. This is the Z which is computed with this perturbed potential. So it's not ZV, but it's ZV tilde. And let's say V tilde is V plus this theta phi 4. Okay, V phi is h minus 1. Okay, so with the weight rho. Let me write. Okay, I think this is okay. This is this digested computation. I think in our community, it took a while to realize that you should do this. Okay, this is the right argument. Even if you use the parabolic stochastic quantity Langevin equation to describe this measure, then if you want to estimate quantity like this, you should not use the solution and average this, but you should look at a new Langevin equation where you perturb the potential. Okay, so this is the point. Okay, this inequality, you see the problem disappears somehow. What was an exponential function become a power. Okay, so for example, Gaussian free field is integrable at the power 4, but is not integrable in the exponential power. Okay, so this, but of course, where is the price you paid? Of course, you have to pay always a price, otherwise you are doing something irrelevant. Okay, so there is a price to pay, and the price to pay is that now you have to control a more difficult object where, these appear. Okay, these appear with a minus. Okay, this is important. Sorry, let me, otherwise would be easy, but the point is here, if you do things correctly, here you get the wrong sign. Okay, you are, now your potential, you're pushing down your potential. So the only thing that saves you is that inside here you have a phi 4. Okay, so you have a, well, you have a pointwise phi 4. Okay, so this is not pointwise. Okay, this is like, you take phi, you take some negative Sobolev norm, which is like integrating phi in some region, and then you take the 4 power. So the 4 power is outside, is in the good direction for Jensen inequality. Okay, so this is controlled, this has to be controlled by all the other terms. Okay, so if this happens, then you can run again our a priori estimate and you get a bound. Okay, so this is controlled. Well, actually is h minus 1. Of course, you need, why you cannot put better, why I cannot put L4, for example. You cannot put L4 because the measure, you have still the Brownian part, okay? The measure, the Gaussian free field is not supported in L4, okay? And you cannot split this because these appear together here. Okay, so you see that, so you have to use a negative regularity norm because of that, because of this, but the integrability comes from that, essentially. So this is controlled by, essentially, Z to the L44. Okay, so we are okay. If theta is small, that's why theta has to be small. If theta is small, this is bounded from below again, okay? So if theta small, a priori estimate for this perturbed T are working, still works. This is exercise for you. This is really exercise. You go back to our computations and you try, and you see that this will not change anything because you can reabsorb it with the L4, with the part of the L4 power. Okay, that's why it has to be small. Okay, so yeah, I find this argument beautiful. Okay, because transform a problem of integrability into a problem of analysis another time, and you see that this tool is not that you can do, you can prove the measure exists, you can really extract information about the measure in a really efficient way, okay? So this was, the intermezzo is finished here, so I think okay, this finished the first 5 minutes of the lecture. In my mind, everything was like that. So yeah, in 5 minutes I do this, then I do that, and then. That's fine, okay? Just my mind is not working. Okay, so this intermezzo, I think, yeah, I still need to finish the proof of, I want to use this formula now. We have to give a different name. Let's, no, this, have to use, we don't have enough symbols, I don't know. So I want to use that formula now. Let's go back to large deviation. Okay, remember we had this function phi of f. Okay, which for every phi, essentially z infinity, z0 was s of phi of f. Okay, this is what we obtain in large deviation. You take the limit. And now remember, okay, what was our problem? In large deviation, our problem was exactly to take the limit of those functionals, okay? So the large deviation problem was like taking the limits as h goes to 0 of essentially W of f with the h. Okay, so the right functional W of f, which has this form. I cancel it, but essentially has this form where you put f here, so you want to take the limit of this function. Okay, and I told you that I have a very nice representation of that functional. I have this representation. For example, I can use this. Okay, so this is the limit as h goes to 0. So I use this representation of the integral in a parameter, this fictitious parameter of the expectation of z, and then there were h, and then, so I have to write h, but I have the perturbed potential. Sorry, I have f. Yeah, and there is the w, sorry. Forget always. Here there were also w. Yeah, and here too. Okay, so I just used this formula before the limit. Now you have to trust me that you can take the integral inside the limit. So this is the same integral. But again, you have tightness. These functions are continuous. Maybe you cut them if you need. But and then you just, so the Brownian motion disappeared. That's why I was ignoring it, because it has h bar in front. And then this converges to essentially z0 of v plus alpha f again. Okay, so the potential plus. So the limit of the phi 4 with the perturbation. This is what I mean. Okay, yeah, actually this proof I can even finish. Good. I cancel this part because we don't need anymore the exponential integrability. Actually, we don't need anymore those formula because I used it. So let's go back here. But we know who is this is f of phi of alpha f. Okay, because the only thing changes is that the test function I multiplied by alpha. Okay, this was exactly this. Because it was at time 1, so the time does not count anymore. Okay, this was time 1. So it's exactly that. Remember, this is the solution of an elliptic equation. Okay? And now there is no expectation anymore. Okay? Now this is a deterministic quantity. Okay? And now you do this integral. You do, now you check. I mean, you write down this quantity, and you check that this is exactly the infimum over psi of the variational problem. Okay, the number you get here is, this is the f prime, was the, no, f, okay. You check exactly that this is magically the infimum of this function. Okay, so this is a computation. Now you get a number here, you get a number there, and you compute them. One way to see, for example, is to add alpha here and to differentiate this. You compute the minimum of the variational problem, you differentiate. It has to be done because it's a family of variational problem, but essentially you check this, okay? Again, this is an exercise. This is an exercise now, a fixed exercise, okay? You have solution of elliptic equation, which are minimizer of variational problem, okay? Remember that phi alpha e solve 1 minus. So this is a nice exercise if you want to do it. Yeah, probably there is, let me put 1/4 here, otherwise and then there is f prime of phi equals 0. Sorry. So this is the solution of this problem with the alpha, and it's a minimizer optimized. So this is this is the Euler-Lagrange equation for a convex variational problem. Okay, the convex variational problem is exactly that one. Phi 4 over 4 alpha phi. Okay, so this function is the optimizer of this variational problem. And then you have to check that if you integrate in alpha, you get the value of that variational problem. Okay, this is a computation you can do. So and this finished the proof of large deviation because you got the expression you want in the limit. Okay, so you go in at finite h, you go in Euler-Lagrange equation, then you take the limit, and then you have to integrate the Euler-Lagrange equation to go back to the original formula, and then you end up with this function. Okay, so this is more or less the idea of the proof. Okay, I have 22 minutes. Are there any? I've been a bit fast, so maybe you should ask questions so that I go back. Just toujours yeah, always questions. Yes.
You mentioned other constructions of this field.
Yeah.
But this seems a very convincing argument for this approach, because this would not be possible with the other.
Well, I think in every construction you can do. I think large deviation, for example, with Langevin, you can do the large deviation of the Langevin and then deduce the large deviation of the measure. I find, so it's not that you cannot do anything in any approach. I think every approach, somehow you can derive some consequence. For me, is mostly the fact, I'm not even advocating totally with this because I have a lot of open problem. Why I decided to show you this is because it's very different from every other things I saw. You think of like Langevin equation. Yeah, Langevin equation, you know. So it's a setting where you start from very different things, but you use semi-basic ideas, that is a priori estimate. So you use PD kind of ideas, and you do stochastic analysis again, okay? You don't do probability. You see, you have a problem in probability theory. You convert into a problem of analysis. Now the problem is not to estimate integrability, it's to prove that this object can be controlled by a priori estimate by the other. Okay, so if you think about it, or if you think how you approach problem in probability, then it's totally different universe, so it can give you different tools. So this was an invitation to think in different ways to problem in probability. And also, for me, this is a way to interpret the original idea of Ito. Okay, at the end of the day, Ito idea is not stochastic calculus. Stochastic calculus is the tool to implement the idea, and the idea is I want to study and I want to understand the sample path of the stochastic process, okay? You want to understand the tick points of the Brownian motion or things like that, and this knowledge, this is unnatural from, physicists don't do that because it's unnatural outside mathematics because you don't see the sample path of the processes, you just see observation, you see finite dimensional distribution. So physicists never look at the sample path of those fields. So this opportunity to use PD idea, it's missed because if you don't look at the path, you don't see very well what's going on. Okay, that's, okay, so just a way you can do similar argument in, I feel this is very compact. This is very compact, especially in infinite volume. In infinite volume, you don't have the measure. So if you want to do large deviation, I think usual thing people do, actually I don't know how people do this, but probably you have to prove finite, you see, you have to prove that for what you are interested in, you can put a finite volume and you lose a bit, only a bit, and then you, well, so it's not satisfying as an approach, okay? I like this, and this is very compact. And I understand, I told you, okay, in this, it's very intuitive what you have to do to prove things in this approach, because then you see the sample path, you imagine yourself as the field who's trying to do something. And this is very useful in. Okay, so let's So I finish last deviation, I give you this idea. But insist this exponential integrability, I know because I try to do it for example, in the parabolic equation, this took at least a couple of years to get the right approach. It's not obvious. You say, well, it's obvious to do that. Well, when you are in the middle of the research, it's not so obvious if you don't get. So in the parabolic case, for example, was a paper of Heirer and Steele who pointed out that this is the most efficient way to do this kind of things. Okay, so find. And as Justin showed with his course, I mean, easy idea, seems, I mean, everything is trivial, but it's 2025, okay? It's not, I mean, Bakri-Emery is in the, I guess, 90s, I think. So it took a long time to get the right proof correct and maybe also to get all the simpler ideas. So, yeah, I think, okay, I was over-ambitious. I said today I start with 543, but let's do the exponential model a bit so we see a different model in two dimension where it's easy. So let's look at x beta phi 2 model. Okay, so this is a different two-dimensional model. Now you are expert of this notation. But the interaction is an exponential, okay? If you have been to Felipe's talk yesterday, no, the other day, then you have seen the exponential of the Gaussian free field, and this is the basic object. So I will not say many things, but I just want to present this model. So I just want to be sure that I'm using the notation in the notes. Okay. So in this model, we are in two dimension and the potential. We are in finite volume, but we do the finite volume differently. That is, we use some kind of cutoff. This is another way to do the finite volume. Okay, you put a cutoff function, and then here you put a renormalized exponential. So this is, so what is this notation? So what is this notation? So we have, so this is the goal. I want to renormalize. So this is, yeah, what is called weak renormalization. I will explain. Okay, so essentially I want a potential which is the exponential of my field. Okay, it's positive, so it's bounded from below. That's good for us because you remember we have problem with integrability. Otherwise, I put that this is a compactly supported function just so that the integral is finite. I have some chance that this object exists. And I want to, essentially, the infinite volume limit is when this function converges to 1, okay? This is infinite volume limit. Okay, but for the moment, let's keep it fixed. We have to understand what happens with the interaction, because I want to put here the Gaussian free field, remember? So I want to understand the exponential. So let's take phi to be the Gaussian free field for the moment. And then you look at this object. This is the exponential of beta phi, okay? And again, you have this problem that this object does not exist. So you regularize, you put some regularization, and, okay. So this is the regularized Gaussian free field. And then the point is that when you take epsilon to 0, so this object is positive, okay? And this is converging to a distribution. So it cannot do many things, okay? It cannot oscillate because it's positive. So something has to happen. And if you try to compute moments of this quantity, you realize that the moments diverge, okay? The L2 moments, because the covariance, we could try maybe to compute. Okay, let's try to compute just to have an idea what happens. Okay, let's try to compute, for example, the integral of exponential beta phi, so some regularization with some function, then you multiply with some function, you integrate, and then you want the variance of that, okay? Well, actually, let me just compute that to the second moment, okay? Just to understand what is the size of this object. And then, okay, you have two integrals, so you have fx and then fy, if you expand, and then you have the covariance of exponential beta, and then you have two Gaussians, so this is this plus the other one. Okay, so this is just I expanded and I put together. Now, I mean, you know everything about the Gaussian. This is a new Gaussian with a different covariance because it's a Gaussian free field. Regularized, okay, so there is no problem. Okay, so this is a Gaussian random variable. You take the exponential, so this is the moment generating function of this Gaussian, and this is the exponential of what? A lot of stuff is essentially the exponential of beta square, well, the variance of this sum, okay? Because the beta square over 2, actually. Okay, this is Gaussian computer. Now you have to compute this variance. You have to contribute essentially the square because it means 0. So you have the contribution from that square, the contribution from that square, and then you have two cross term, okay? So this gives same thing, and then exponential beta square over 2. Actually, the 2 disappear because you have beta square. You have two contribution. So you have the covariance, let's call it C epsilon 0 for the square of this and the square of this. And then you have the covariance between the two. So you have C epsilon x minus y. Okay, so this is the covariance, and I remove the 2 because you have two contribution of each. Okay, so this is a computation. And now you have to recall what I said about the regularized Gaussian free field in two dimensions, but essentially C epsilon x behave like 1 over, behave like the log of x. Yeah, now I forgot the constant. Felipe, what is the constant? Where is Felipe? 1 over 2 pi. Yeah, or 4 pi or 2. I don't remember. Okay, there is a this is important so that's why I'm insisting in the constant. And then you have the regularization. So maybe this looks like this. Let me think. When epsilon goes to 0, no. Yeah, then there is a minus overall. Sorry. Yeah, something like this. Okay, it's not very important. The only thing important. It's the only time I care about the constant. Okay, so this covariance is like this. So when you go here, so remember this. So when we go there, we have double integral something, and then you get here there is no position, so you have only epsilon. So this is a log epsilon. Beta over 2 pi. I think I got wrong the constant, but so you have epsilon. So this is epsilon minus, yeah, good, beta square over 2 pi. Yeah, I don't remember the constant, so don't trust me about these constants, okay? But certainly you have a term like this, which is coming from that, and then you have something which instead of epsilon, now I ignore epsilon. Let's say I do one up. Okay, I can keep epsilon. Here you have epsilon plus x to the power, again, is the same minus beta square over 2 pi. Sorry, here is x minus y. Okay, this computation is just to give an idea what is this object. Will not give us much more than that. Okay, but let's try to. We will tell us some difficulty, and we tell us something about the first thing is that you see, I get this divergence. Okay, So this is diverging because I have a minus sign, so this is not good for me. This quantity will have a size which is diverging with epsilon. So this suggests what you have to do in life is that you don't want to consider this, you have to make it smaller, and you have to multiply with exactly what compensates for that. Yeah, maybe it's the right thing to... and the other thing will happen, it's very bad news for us, is that when epsilon is going to 0, this quantity is not integrable if this is, you see, we will have problem of integrability when this quantity is on the diagonal, we are in 2 dimensions, so when this quantity is bigger or equal than 2. Okay, because then this will become minus 2, and in 2 dimensions this is not integrable. Okay, so this will give something like 4 pi. Okay, so problems. Okay, so yeah, okay, problems. So this quantity is not integrable. Even if I remove this by multiplying, I still have this problem. This I cannot solve. Okay, so this gives you a feeling that there will be problem of integrability, so the L2 norm will still diverge, and but this is give the renormalization. Okay, so renormalization can be cured. So what I'm doing here is that now you define. So you define the renormalized exponential. So what is this symbol here? It's just what we did with the weak products, is that you define this object to be the exponential of the Gaussian free field, and then you multiply with this constant, but if you think about it, is exactly subtracting the variance of the Gaussian free field. Okay? So the expectation of phi in a point squared. Okay? So you see this is some kind of, this is natural object, for example, like a stochastic exponential for Brownian motion or things like that. Okay, it's a natural object. And this is actually, you already seen this quantity. So this will cure this problem, but will not cure that problem. Okay, so let me say something about this quantity. This quantity now is of this form. If you expand it, you will see things you like very much. You have Bn and factorial, and here you will see the powers, the renormalized powers of phi. Okay, so this correction you added when you expand in beta, it composes exactly and give you the Hermite polynomial. So I wrote a formula like this, and when you apply here, you get that. So you can guess already from this formula that this object will have a limit, maybe in the space of distribution, because somehow these objects are distributions which are converging. And actually, in L2, somehow they are orthogonal in the L2 space of the Brownian motion. So somehow this object will have a limit. The problem, so essentially, there exists the limit. Now, there exists a limiting object when you do on the Gaussian free field. And this is called the stochastic, in the sense of distribution, it will exist, okay? But it's a bit, so in theory, it's an object like this. Now, you have to be more careful because, of course, of this problem, and then the right way to do it is that this object, you see, if it has a limit in the sense of distribution, okay, let's say in S prime of, let's say, R2, okay? This object will be a distribution, but it's a limit of positive quantity, because here, you see, the point here, the renormalization didn't spoil the positivity, okay, and didn't spoil the convexity, actually, but this is less clear what does it mean, convexity of this object. Let's say didn't spoil positivity, so it's a positive distribution, and therefore is a measure, okay, it has to be a limiting measure. So there exists an object, maybe you know, that is called the Gaussian multiplicative chaos, which is this limit, so it's a random measure, which depend on beta. Yeah, you define it in this way. You integrate, well, you define it as the limit, as epsilon goes to 0 of things like that, okay? Of dx. Okay, so you define this random measure. Yeah.
Maybe just for the constants, so I think it's the right one for C epsilon, but then there's a 2 coming from what you raised for the right, so it gets us 12 over 4 pi. So then when you compare the 2,
It's probably, but I think I did correctly, because you have 1/2. I mean, I could agree with you because I had some doubt, but I could not find the error. I had 1/2 from this, and then I have 2 covariants, so this removed the 1/2. So,
it's 4 pi in the end.
yeah, we don't care. I mean, I think this is fine, because this is telling you that if beta is smaller than 4 pi, the object is in L2, which I think it's okay. Okay. So this random measure exists for every beta square less than 8 pi. Easy, and for 8 pi, again, and I didn't know about it, but Felipe told us about the connection between this and the points where Gaussian free field is very large. But we don't care about this. So our object is we want to construct some potential, which is this exponential. Why I want to do exponential? Because I know how to renormalize it. Okay. Again, okay, it's not here. We are not doing. Yeah, time is finished. So maybe we'll continue next time. It's not that, I mean, why you cannot do different functions, because I don't know how to renormalize them. I don't know if they exist. But certainly the exponential, I can prove it exists. There is a beautiful theory. You can look in the book of Powell and Beresticki, for example, but this is a nice place to see. So you have this measure. So let me maybe spend 1 or 2 minutes to write the object we're interested in, and next time I continue. So the plan is I choose this renormalization. I know the object exists, at least on the Gaussian free field. And on finite volume is actually even easier than 542, because this measure, it's finite. So, okay, what you can do is just define the measure. For example, in finite volume, you can just define the measure nu psi to be the exponential of minus the integral of psi with respect to the Gaussian multiplicative chaos. So this is you have to think this is a function of the Gaussian free field. So this is a random variable, okay? So I see it as a property of the Gaussian free field. It's a measurable function of the Gaussian free field because it's limit of measurable, but it's not, you cannot express as a continuous function of the Gaussian free field, okay? You lost. But you have to think that depends on the Gaussian free field. Then I integrate my cutoff. I integrate over all the space. This is, you can check it's a finite quantity. And then you just weight with this quantity the Gaussian free field. Okay, so you want to construct a tilt using this thing, and then you divide by a constant which depends on your cutoff. Okay, this is the finite volume 5-4. Okay, exponential model on finite volume. Okay, so I cannot, this is even easier than 5-4 because this is positive, so this random variable is integrable, and then you bring the expectation, it's positive, and the other property you know is that the expectation of this measure, it's useful, now you compute the expectation of this measure, and this is exactly the Lebesgue measure, okay, so the expectation of this random measure, when you take the expectation of this is 1, because it's normalized to be 1. Because of that, that's why I choose this to be the full green function, not only the singular behavior, okay, just for this. And then you have Lebesgue measure. So this object exists, is finite, if psi is integrable. So by Jensen, you have a lower bound, so this is not 0, and you have an upper bound because it's bounded by 1. Okay? So this is even easier than 5-4. We don't need Nelson argument to construct the measure in finite volume. But then now the problem is how I take the infinite volume limit, and tomorrow or the day after tomorrow we will use the variational formula to do it. And I want to do it because in this case, in infinite volume, there is a unique solution. So I can say that the sequence converge. Okay, stop here. Do you have questions before everybody? Ugo, you have a question? Are you sure? Okay. I don't remember other names now. I don't know why I remember yours. So yeah, of course. Okay, are you sure? I've been a bit fast, but no, please ask one question, otherwise we don't leave. I want a question. Yeah?
I didn't understand initially when you brought, when you integrate over the measure mu of e to the minus f.
Yeah?
When you make this, how the second term appears, which is the integral of e to the minus v d mu.
So I was looking, so you mean the integrability or the large deviation?
Here it's f d minus f d mu, right?
And nu. Yeah,
And then you, so it's minus log.
yeah.
And then, so the first term I understand here is minus integral of e to the minus f multiplied by the exponential of minus v.
Yeah. Ah, the second term is because this measure is normalized. Okay, so you have this, but there is z. So what is z? Yeah, thank you for the question. I've been fast. Z is really the integral of v, the mu. Okay, so the second term, when you take the log, it goes into minus, and then this becomes the second term. So you have a term where you have f plus, so this will become the integral of f minus v with the log, and then you have another term with the log of minus v. Okay. Okay, it's enough. Thank you. Question?